Right.
You're good to go.
Got it, Zoom. Thank you. All right. Welcome, everybody, to Disciplines 101. This, for those of you that might be new or have forgotten in a couple of weeks, this is an activity of Seacoast, which is the Collaboratory for Coastal Adaptation over Space and Time, a research coordination network funded by NSF. And in this Disciplines 101 activity, we ask researchers from very different disciplines to teach each other about how the coastal world looks through their disciplinary lens. What are the main methods and approaches that their discipline uses to address coastal processes and issues. And we have the goal that with sharing our different disciplinary perspectives, our different lenses, we can ultimately start to forge new combined perspectives, forge new lenses on the coastal processes and issues that will be transdisciplinary and get us to new places for new science and new potential ways to help the system work in ways that we like better. And today, I'm really excited, we have lessons from Patrick Barnard and Sarah Shoshani, and I'll introduce them one at a time, and we'll have something like 20 minutes of lesson from each of them, followed in each case by 10 or so minutes of questions. Just some logistics. Catherine Enarde will moderate the questions, and she'll prompt you close to the end of the presentation to put questions in the chat. You can either volunteer to ask them yourself, or if you'd like to send them privately to Catherine, she can ask anonymously. And let's see, well, on the question front, we'd love to get questions from as many of you as possible and outside of the usual suspects. Some of us are too noisy, and we'd love to hear discussion that brings in people from as far abroad of our usual question askers as possible. And just we're evolving into this Zoom world in different ways, and I think it's become more customary to leave cameras off and eat lunch during a midday seminar, which is understandable. On the other hand, the more of us that can leave our cameras on, the more like the old real world before Zoom that it can be, giving a presentation. And it always helps to see the faces and reactions of the people that you're talking to the extent that that's practical for y'all. Okay, Patrick, do you want to share your screen, and I'll give a brief introduction. So Patrick Barnard got a bachelor's degree from Williams College and a master's from University of South Florida, and then the PhD from UC Riverside. Patrick is broadly a coastal geologist. That's his title with the USGS, and has been for a number of fine years of science, where he's addressing storm and climate-related changes to coastlines, beaches and cliffs, and coastal communities and estuaries along the Pacific coast, fairly specifically, but we'd love to think about how all that relates to our coast and our different disciplinary lenses. So with that, I will turn it over to you, Patrick. Thank you.
Thank you. You can hear me okay? All right, great. Thanks. So I really want to talk about coastal climate impacts, and really key question is, how do we make this work relevant? And we built a lot of this work on the West Coast now, but it is going to the national scale in various forms. We currently are building out similar work you're going to hear about today in the Southeast Atlantic, and we're looking for collaborations and new ideas of how to really push the science to make it meaningful for decision makers. So we have a new programmatic focus within USGS and the Coastal Marine Hazards and Resources Program, and this is this symbol down here, coastal change hazards. And the concept is that, we're not living in a research bubble. There are products that go out to users. It's a swirl of feedback that is critical sort of interface to make this science meaningful. So there's dozens of people have contributed to this work from all over USGS, really all over the world. We've been looking to try to get the best science wherever it is. And so keep that in mind as we move forward as well. Just a little tiny background about myself and how I got here. I'm a research geologist and I lead our climate impacts program, but I grew up on the beaches of Southern California, and my earliest memories are of the 1982-83 El Nino, which took out a bunch of my favorite piers, caused a lot of damage and destruction, about $2 billion across California. So that's when I really first became sort of enamored with the power of the ocean and how the coast responds. After undergrad in the Northeast, I made my way to Florida, where I looked at the anthropogenic influences on barrier island and inlet evolution. And there's no better place than the west central coast of Florida, where there's been just massive perturbations to the system from fill causeways and jetties and beach nourishment, and just the speed of response of the coast to these interventions is just astounding, and really fascinating area to work. And of course, you've got the looming threat of hurricanes and having to deal with that across this system like you do in a lot of the Southeast Atlantic as well. Took a bit of a detour after that, doing geomorphology on a wholly different environment. I had an opportunity to work in the Everest region of Nepal to look at paleoclimate reconstruction and hazards across the Himalayas. So I jumped at that opportunity, looking at natural hazards across the spectrum, really. We looked at, we were there post-Chamoli earthquake in '99, looking at earthquake damage throughout this region. And in particular, looking at earthquake-triggered landslides and monsoon-triggered landslides across the region. But the thrust of the program was to look up in the high mountains and look at the response of the landscape to significant climate variability, in particular glaciations and deglaciations. So did a lot of mapping, a lot of geochronology, a lot of geochemistry. We dated hundreds and hundreds of rocks to understand the timing of these different events. My particular focus in the group was looking at glacial lake outburst floods and how it affects the valleys below the heads of these glaciers and their timing. And so this is up near the Everest region, a large dammed glacial lake. And we think in the past, based on the geochronology and the mapping, that all these events were happening synchronously across much of the Himalayas. And so it's a different kind of look at how the climate drives landscape response, but it does just the same. So this was a pretty incredible experience, though I did have my share of sketchy bridges and sketchy airports. And if you haven't flown into Lukla in the Khumbu area and landed on a runway with a 10-degree slope and you take off, you go right off the edge of a cliff and you see the wreckage of planes below and you realize that, maybe I don't want to be doing this for the rest of my life. Also worked in the hyper-arid part of Tibet, so looking at paleoclimate reconstruction in a much different setting, although nearby, but hyper-arid. But my love was in the coast, was able to make it back to the USGS as a postdoc. In part, I'm told, because I wrote a lot as a graduate student, that served me well. I think even though I wasn't specializing in coastal at the time, I think it might be hard to do that today. There's just so many uber qualified candidates with a specialty in coastal hazards that making that transition probably isn't as easy as it was now almost 20 years ago. But to the matter at hand here, and a lot of the focus of the last 10 years in my group has been looking at coastal hazards and climate-driven coastal hazards. And so the big question is, why is this relevant? Well, we're on our way to having 1 billion people living in the coastal zone. And with accelerating sea level rise, the once in a lifetime coastal flooding event is going to occur about every year by 2050, every day by 2100. So a place like Ocracoke here in the lower right, what we saw during Hurricane Florence is the kind of thing we're going to see maybe on a monthly basis down the road or on a daily basis down the road. So how are we going to live with these kinds of hazards? But when you consider storms and coastal change, the coast is not static. Work we've done shows that about 3 times more people would be at risk. And for the US, just the static effects of climate change in terms of sea level rise, on the order of 10 million people will be at risk by the end of the century, not including storms, not including coastal change. So it's a big problem if we do nothing. And we've tried to relate this in California to dollars and lives in particular, and looking at exposure. We're talking about just in California about $200 billion in property, which is about 6% of GDP. And we've tried to relate this to other hazards in California in terms of these massive wildfires we've had. These numbers are about 10 times greater than the worst wildfires and earthquakes in California history. So it's a significant problem that needs to be addressed. And that's kind of the point of this, but it's not a dystopian future. These kinds of impacts are happening now, and it doesn't matter if you're in California, if you're in the Pacific Northwest, if you're in New York in the Northeast, the Outer Banks of North Carolina. Places like Miami are having daily impacts from high water levels, daily flooding in neighborhoods. Just last month, we had another major hurricane roll through Louisiana, which ended up having significant impacts in the Northeast as well. So this isn't just some future where we should not be accustomed to. We're seeing these impacts today, and they're just going to become more and more frequent as we move forward. And some of these impacts are going to translate further landward. So the question is, how do we address this, and how do we map these hazards today and in the future? And we began this work. The only models available were basically bathtub models, looking at sort of the static impacts, just raising the tides, raising sea level, which is a really nice way for looking at the daily impacts of sea level rise. So it's a really nice screening tool, but it's going to underpredict flooding hazards because it does not include all these other dynamic drivers of water levels along the coast during extreme events. Just an example here from Foster City in the San Francisco Bay Area. If you look at, just 25 centimeters of sea level rise, we have an area protected by levees. The green are areas that are below the flood level. So imagine this is New Orleans, protected by levees. But when you add a storm to the picture, the hazard risk goes up significantly. So that's what we wanted to bring to the table. This is why we developed the coastal storm modeling system, to bring all the physics in, bring in the seasonal effects, bring in the storm surge, the river discharge, the waves, and also consider that the land is not static. It moves up and down and also responds laterally as well to oceanographic forcing. So I want to include all these different physics and have a really comprehensive assessment of present day and future risk. So over the last decade, we've been building this system out, and it really kind of brings to bear this concept of multidisciplinary science. It takes a lot of expertise to do this work. So we start at the global scale, grabbing the latest wind and pressure fields from CMIP-5 and CMIP-6 global climate models. This gets fed into global wave models, which are then downscaled to the regional level, where we bring in tide models. We bring in the regional forcing in terms of storm surge and locally generated seas. Then all this gets ultimately downscaled to the local level, where we've been transform the waves across the inner shelf and across the surf zone, and also the setup and run up of the waves across the beach and the response of the beach and dune system. In parallel, we're also looking at long-term cliff recession and shoreline change. So we need to develop models for that, so that we're actually evolving the coast through time, in addition to just the storm response itself. All this is done, it gets put onto a high resolution digital elevation model and put out into some web tools, which I'll talk about in a minute. Let me just make sure I've got my timer here so I don't go too far over. Okay, so one of the many pieces that goes into this work first is we need a really high resolution, accurate digital elevation model. So there's lots of work here dealing with geodesy and surveying and trying to grapple with pulling together, in some cases, 50, 60, 70 different data sets to make a seamless terrain map. Because the model is only as good as the elevation, and the elevation isn't good, then all the physics in the world isn't going to get you anywhere. So this is a really pretty huge effort as part of this work. And so we have 1 to 2 meter elevation DEMs wherever we go, that they're a foundation for all the modeling. And then is the task of building out model grids, nesting model grids, making them efficient, making them stable, testing them, and making sure that we're we're using all the available information, oceanographic conditions, waves, tides, so the models are working accurately. And so we have confidence when we're looking at the future. And as I mentioned, in parallel, the other really key aspect of this is how is the coast evolving through time? We can get the water levels right, sort of in a regional, local scale, but we really often need to know how the coast is changing. And so we had a postdoc, Sean Batusik, came on and developed this model for looking at shoreline retreat over time. And he leveraged this extended Kalman filter method of long implant. And what's really clever about this approach is that in any model, we have free parameters, which we're just guessing at wherever we are, based on things like beach slope and grain size and parameters like that. But we don't really know, and we don't have data everywhere. And so what we've done here is whenever there's a data point, either from LiDAR or a survey, this auto-tuning approach adjusts these free parameters whenever there's a data point to match the data. And then once we run out of data and get into a forecast mode, we have a tuned model every 100 meters along the entire coast. So this is being done at a 50-meter scale for the Southeast Atlantic right now. In some cases, we might have 2 or 3 data points historically. We might only have, and this is a case we actually have about 24. So we've moved now toward accessing the satellite record, which has been a huge improvement in this work. And so now we can mine the Landsat inventory. We can go back all the way back to 1986. Sentinel goes back a ways as well. Now there's high resolution satellites at sub-meter scale with daily passes we're working on mining. So now we can adjust these models and auto-tune them with a lot more data. Now, instead of maybe 2 data points, 10 data points, 20 data points, we have a minimum 500 everywhere. And ultimately, we want to be able to do this on a daily basis at the national scale. So we can tune these models, we can update them on a daily basis, and make forward projections from days to decades. That's the ultimate vision, but it's a big data problem that we're trying to work through right now. It's just an enormous amount of information, and we need cloud solutions, and we're working on that and looking for help with that. And so this ultimately, these shoreline projections get put into a Google Earth type interface that people can view or download through a GIS and look at the impacts through time. And it's sort of a similar approach, but a little bit different. Brad's former student, Pat Limber, came on as a postdoc as well to look at cliff retreat through time. And the idea was to use a model ensemble, so 5 to 6 different models, run in a Monte Carlo simulation, varying all the free parameters. We run each model 100 times for every scenario. We group them by agreement. It's weighted by agreement, so we end up with a median projection of cliff retreat and an uncertainty band, and so this gets us better, a little bit nicer into the probability space. And these models are driven by essentially by wave impact hours at the cliff base, as well as are informed by the historical rate. So it's another approach where you don't have a lot of data here, but to make a forward projection with some confidence. And when you start mapping this up in California, you understand very quickly that there's lots of cliff top construction, development, infrastructure at risk over the next century if we don't do anything. So all this gets put together, the coastal evolution through time, and then we bring all the oceanographic forcing into and look at usually about 40 different scenarios across the California coast, and we're also building this out in other areas, as I mentioned now too. 10 sea level rise scenarios, 4 storm scenarios, all the different forcing all comes together, and ultimately gets put out into this this user tool. Initially, we put out in Google Earth just files, simple KMZs, KMLs, or we just serve up the GIS files, which you do anyway. But most people can't deal with 20,000 GIS files, so we built this interface with our partners at Point Blue Conservation Science, and so all the data is served up on the fly. You can click through these different scenarios to whatever you want to look at, whether it's today's big storm, tomorrow's big storm, tomorrow's sea level rise with no storm. You can look at wave conditions, current conditions, duration of flooding, uncertainty, etc. You can download data, upload shape files for jurisdictions, lots of bells and whistles, which I don't go to in too much right now. But people go to the area of interest. Here's just an example from Newport Beach in Southern California. Start clicking through scenarios, looking at tipping points, looking at trigger points, where are we going to start to see our exposure increase dramatically, and begin to make plans accordingly. So that's the whole foundation of that particular work, and it's really gotten the science out to a much, much broader community than a few academic papers and some KML files. Also uncertainty, so looking on a regional scale here at Orange County, uncertainty is really important. It's important that we're very honest about what it is. And so we know the vertical land motion is causing some uncertainty. We also know where there's uncertainty in the model itself and also in the elevation data. And so we always provide this layer of, what's the worst case scenario, like a 95% confidence band, which people use in varying degrees depending on the sensitivity of their infrastructure. And then the next point where we're trying to translate the science and really get people to wrap their heads around it is looking at societal impacts. And so we developed this tool known as the Hazard Exposure Reporting Analytics tool. And what it does, it's an exposure tool which looks at what's in the hazard zone. Very simple first order approximation. So now instead of looking at this sort of flat, 2D flood map across California, we can now translate this into dollars and lives. And it's really moved the needle, I think, in terms of how the states responded to this potential risk. And I'll talk about that more in just a second. But in all this outreach work, we've invested a lot of money in outreach, a lot of resources, which is really critical. It's informed the science as much as it has supported sort of decision-making. We realized groundwater was an issue, and a rising water table with sea level rise could be a significant problem for a lot of these coastal communities. The basic concept is that, the water table on the coast is set by the recharge, the hydraulic conductivity and sea level. And so if sea level goes up, the water table has to go up at some rate, not necessarily linearly, but it can ultimately have issues for communities. So we reached out to Kevin Beefus, University of Arkansas now. He built mod flow models across California and looked at a bunch of the same sea level rise scenarios to look at the exposure of a rising water table along the coast. And what we found is that in some communities, and Pacifica here is an example, may only be vulnerable to an extreme storm over the next century. But when you consider the water table here in the middle, it already has a very shallow water table. And as we move through time, that water table may emerge at the surface and cause daily impacts to this community well before we have daily impacts from sea level rise. So that was something that we learned. It's highly variable across the California coast. This all gets put into the same web tool. This is now the version 2.0. And this is a very similar picture across the state where you've got high marine terraces are sort of safe from this hazard, but these very low-lying areas, basically reclaimed estuaries, are at risk of this groundwater rise across the state. And so it's another hazard to put on the map for people. But it kind of also begs the question of, what are the impact? What does this really mean? We looked across the state, there's almost an order of magnitude more potential exposure from these groundwater hazards compared to overland flooding. But what does exposure mean, and how does that translate to hazards? We know basements can flood. We know this can damage utilities and sewage systems and roads, but there's not a lot of data or science on this. We really don't understand what these impacts are. So that's the point of research. And then, these large scale coastal adaptation measures, typically we think of things like retreat, although that's a bad word. We don't say that openly so much in the communities now, but, we can elevate, we can block overland flooding, we can restore shorelines with green solutions, but where does this leave groundwater? Groundwater, doesn't care about some of these solutions. So how are these strategies going to work as we move forward? And there's a lot of science needs to be done on this front. And I'm going to run out of time, so I'm just going to touch on this very briefly, but this is another way we try to look at the concept of coastal systems and different disciplines and how do we really assess impacts. So this is a paper I'll talk about at Ocean Sciences. Some pilot work in Santa Barbara, where we looked across different systems, tidal marshes, beach ecology, the built infrastructure, to look at where these inflection points are in the system. And this is what this graph over here shows. And just to highlight quickly, essentially, the ecosystems their health is plummeting immediately. Just with 25 centimeters of sea level rise, that habitat space is going down to almost nothing. Whereas the big inflection points in the flooding are happening much later, more like around 1 meter to 1.5 meters of sea level rise for this particular community. So the point is that the ecology is seeing threats immediately. The big inflection points for the flood exposure are happening much later. So if ecosystems are a priority for a community, then it's happening right now in Santa Barbara. If flooding is a priority, maybe you have you can buy some time, but ultimately these are all intertwined systems and we have to think holistically. Okay, lastly here, thinking of other ways to communicate the science and really try to make it relevant to people. We've been doing some virtual reality work. We have a couple on tap now, one out in Ocracoke and one down in Miami that we're going to be working on upcoming. It'll be in Ocracoke actually in about a month or so. But we built a similar video. Let's see, I'll go back, I'll play this real quick. I'm probably going to go just a few minutes over, but I'll try not to do more than that. Here's a video we made in Capitola using Cosmos projections, using real-time, elevation, dialed in elevation data to try to get people to really understand what we're looking at in terms, get them immersed in the science and be able to really put themselves in that situation. So this is a 2D version, but you can use VR goggles, you can grab that, and that's when it's really powerful to get sort of immersed in the science and look at what does sea level rise really look like to me on the ground. You can turn around 360 degrees and the sound and everything, it really is sort of more of an emotional experience than looking at a map. So I'd invite you, I think the sound isn't working, but I'd invite you to look at this online and check it out. We got some basically former sort of Pixar animators and others to do this for us to really try and put people in that place and get them to feel what what this is going to look like in the future and where we might be.
All right, thanks, Patrick. Are you ready for questions?
I just have a couple more. I'll just zip through them. Sorry.
No, that's okay.
Just quickly, we also did some augmented reality work. We put this system into one of these telescopes at the pier. And this is a little bit more of an optimistic view of the future, looking at where the conditions are today, looking at sea level rise of the future, looking at the sea level rise plus storms of the future, and then a potential solution. So we got about 10,000 views. People go by, they look through this, they answer some questions, and you get a kind of a sense for what we're looking at. And so this work has been, in some ways successful across California, which is why we're building it out at the national scale. All of this is fed into a lot of climate adaptation work, supporting departments of transportation, Coastal Commission for evaluating permits, and now using a lot of these same talking points here, the state legislature used this information to just pass a $4 billion climate resilience spending package. So it's having an impact, but there's so much more to do. There's so much more we can tap into. We're building some of these efforts, across the country right now, very similar approach. And I mentioned the Southeast is ongoing right now, and it's going to be completed in a little bit, but there'll be lots and lots of work to build off of and go on for many, many years. So we're looking to try to get national coverage for lots of these kinds of products. So finally, kind of where we're headed and future needs, we're going to continue working with stakeholders to support this regional local policy and management decision-making. That informs the science. But we need more interdisciplinary science. And working with Dylan right now on a co-op to look at tipping points, to look at how the real estate market responds to these kinds of changes, and kind of something that really puts it into a more of a societally relevant framework, so people understand the risk. And this will help then again translate the science into societally relevant products. So really we're talking about actionable science is the bottom line. And then really the key too, which has been a big push for this administration, thankfully, is supporting community resilience and environmental justice. Just because we're a public agency, just because this information is available, doesn't mean it's accessible. So we have to really think a lot more about how we can, support grassroots organizations to really get this science to people on the ground, on the frontline communities making decisions. And that's an area of really huge interest for me moving forward, and how we can really move the needle on the social science side, because all the science sort of in a vacuum isn't going to get you anywhere if people aren't actually using it. So thank you for letting me go over by 5 minutes, and happy to answer some questions. There's tons of links. I'll make this available so people can grab stuff if they want to.
Great. Thanks, Patrick. That was a wonderful talk. Okay, we have 2 questions in the chat. Ian, you're first. You can now unmute yourself to ask your question.
All right, thank you, Patrick. So really cool to see that overview, not only of sort of like the suite of things you're working on and have worked on USGS, but also your pre-USGS life, which I'd never seen before. My question was concerning, so you talked about both the shoreline change and the bluff retreat models and mentioned 3 parameters for each. And I was curious if those are the same 3 parameters.
I'm sorry, I missed the last part of that.
Are they the same 3 parameters that you're tuning in both of those models?
No, yeah, right. So the cliff models have a bunch of different, and Brad probably knows as much about this as anybody, have a number of different parameters. Different models have, different sets of variables, so they're not the same. I mean, the general concept is that the more you impact a beach or a cliff, the more it's going to retreat. And that's the overall concept, but the parameters are different for sure.
Okay, our next question comes from Roland. Roland, can you unmute yourself? There we go.
There's less of my background.
Okay.
There's less of my background. I can't.
Okay, I'll go ahead and ask your question for you if that's
Hello,
okay.
can you hear me?
Okay. So Roland, I'll ask her question. He says, one of the crises faced by coastal communities in Nigeria is coastal flooding. Due to the increase in coastal zone population, the government put on a project to reclaim vast areas of land taken by the ocean by building seawalls and sand filling it. This singular act has increased coastal flooding in lowland areas along the coast and also alters the longshore sediment transport in the Gulf of Guinea. What are the possible ways to mitigate these issues?
Yeah, I wish there was an easy answer to that. It's a major challenge. I mean, I think something like 48 of the 50 mega cities, and Lagos is no exception, are built right along the coast in very vulnerable areas without sea level rise. A lot of them are subjected to subsidence due to groundwater pump and other fluid withdrawals, and so they're sinking on top of that. And effectively, seawalls are a short-term band-aid, and we have to think of bigger solutions. I mean, places like New Orleans have been pumping out water for, 100 years or more. Miami is investing hundreds of millions of dollars in pumps right now. They're even considering things like gunniting the subsurface to prevent, the groundwater from coming up from below. We're trying to think of things outside the box. And unfortunately, some of these communities, relocation is going to have to be an option that eventually gets embraced, though we're nowhere near making that a politically viable solution. We're seeing this in Miami, redlining. We're seeing, which side of the seawall are you on? There's a lot of environmental justice issues that are to be addressed. And I wish I had a better answer for you. And so it's such a significant, daunting problem that we have to think holistically about the system. And that's something that's happening in San Francisco Bay now. They're looking at, well, if you put a seawall here, it's going to ultimately affect water levels in other parts of the bay. It can't be a piecemeal approach. It has to be a holistic approach because of sediment transport, because of amplification of the tidal wave and surge and things like that. It's a very complicated, interconnected system. I think we're starting to understand how interconnected these systems are, that, doing something in one place is going to ultimately affect your neighbor.
Thanks for that, Patrick. Following up on that question, Dylan, can you unmute yourself? Or maybe it's not a follow-up, sorry.
Yeah, no, sorry. Yeah, awesome talk. Some of those visuals were really radical. The virtual reality stuff is mind-blowing, kind of. I had a question about public perception. When you put all these tools out there and the public has access to them, are you finding that the kinds, at least to the extent that you're aware, the kinds of people who are looking at these tools are the kinds of people who are kind of already aware of some of the things that are happening at the coastline and are going to be happening? Or are you getting some really surprising public responses from people who are kind of really learning how precarious some of their spots are?
Yeah, I think it's all over the map. I mean, I think we've learned early on that we really need to focus on what's happened in the past and show them images of, oh, I remember the storm last week or last month or last year. I mean, this happened in your community. You know, let's just put this in perspective and not just look at, you know, this sort of worst case scenario down the road. You know, we've been in some cases lucky to be working in California for so many years, and the communities generally embrace all this work. However, as soon as the state or the county has suggested modifications to the system, things that are going to hurt them on a daily basis, then we get a lot of pushback. So very sort of outwardly progressive view of the science and supportive, but the second that people are being asked to, well, we had to think about retreat, then the walls come up and just forget it. People become deniers overnight. It's been pretty startling, actually, and it's totally shut down a lot of conversations in communities like Del Mar and Pacifica, where retreat has to be on the table. But you know, so I think and I definitely get feedback too about like, well, why are you looking at these scenarios? I mean, look at the tide gauge. It's only 2 millimeters per year. How can you get to a meter by the end of the century? You know, where's this coming from? And I think the new sea level rise report that Billy Sweet and Chris Weaver and myself and others are working on, sort of the update to the NOAA 2017, is going to have some projections based on the last 30 years, which is going to push. It's not just a linear extrapolation, it includes acceleration. So we're going to be seeing higher sea level rise, even if you just extrapolate out using acceleration. So hopefully that'll help a little bit with the people that are sort of on the near skeptic side of saying, hey, just going out, we're going to have at least 40 centimeters no matter what, instead of 20, for example. But I think it's a huge problem in how we communicate the science and how we don't just get people to put their blinders up and just discount everything, because ultimately it's going to take personal sacrifice to get us out of there. And I don't think we're ready to do that. And hopefully, like working with you, for example, on things like, you know, what hurts their bottom line? Well, real estate market is one. If people really think that their real estate, you know, prices are going to go down, then maybe they'll do something. Or, you know, transportation infrastructure and all that kind of stuff, things that are going to affect their day-to-day is, I think, when people ultimately are going to hopefully embrace the science and start to make smarter decisions.
All right, thanks for that, Patrick. We need to move on to Sarah's presentation. I know there are some other questions in the chat, so maybe if we have time later, you can email Patrick directly with those follow-up questions.
Yep, thank you.
Thank you.
And I think I probably speak for many of us that we hope to interact as much as we can with you going into the future. A lot of these approaches are really exciting, and we'd love to talk with you more about dovetailing some of our longer term visions into the kinds of approaches you're using to interact with stakeholders.
That'd be great.
And
yeah, please reach out.
It occurs to me that I skipped over the punchline of Patrick's introduction, that he is the research director for climate impacts in the coastal process team at the USGS, which you probably got the sense of along the way there. Now, Sarah Shoshani. Sarah's work to me is very fascinating and exciting, and I was also really fascinated just reading the bio in detail and the names of some of these degrees. So let's see how I can do here. Well, she got a Bachelor of Science and Industrial Engineering from Iran University Science and Technology, and she got another Bachelor of Science in Industrial Engineering from Southern Cross University, and a Master of Science in Industrial Engineering from Purdue, and a MSISEOR, Master of Science in Industrial Engineering, Industrial Systems Engineering and Operations Research from Virginia Tech, and a postdoc from the University of Michigan, Department of Industrial and Operations Engineering, and she has now thankfully joined us in Southeast in North Carolina as a faculty member at North Carolina State University in the Department of Industrial and Systems Engineering. And I look forward to this. Sarah, take it away.
Hi, everybody. I'm very excited to be here. Thank you for the invite, Brad. And I am new to this research community, but I'm very fascinated by the work that everybody is doing, the interdisciplinarity, and just high impact that that it can have for this region and other coastal communities. And I think personally, even though my research is a little less graphical, maybe I have less exciting visuals to share, but I think that there is a lot of potential for what the stochastic simulations optimization and analysis can contribute. So I'm going to start the talk just giving a little bit of a maybe a description that I'm going to give very high level overview of some tools. I'm not going to go into a lot of depth here just because of the time, but I'm happy to share resources if any of the topics that I list here is of your interest. So please feel free to reach out to me, and I have my email address at the last slide. Okay, so I think when I was thinking about the kind of the best way that I can cherry pick the things that I think would be important to share with you all here today, I thought about really the following four main messages. The first one is that a lot of the current practices that are in place because we want to hedge against current risks could actually be worse choices and strategies in the longer run. And that's just because that we ignore a lot of the uncertainty in the future, the behavior of the systems and the behavior of the interactions between things. And I'm going to get a few examples of what I mean there. And the next message is that given that we are in a highly uncertain world, I think one thing that we are more certain about is that there will be a lot more extreme and catastrophic events for which there is not really a lot of data. And I think the previous talk really set it up for me also about the frequency of this issue, where in order to have reliable models, we have to think a little outside the box and see how else we can really strengthen our understandings of the future, given that we are in shortage of data for a lot of these catastrophic events. And that leads to the fact that a lot of the times, instead of common analysis of the outcomes, which is to look at the expected outcomes, in the case where we want to hedge against high risk events, we probably want to focus more on safety, and that translates in a statistical sense into focusing on tail behavior of our probabilistic distributions, and that calls for smarter quantifications of uncertainty. So the usual mean and standard deviation may be misleading, in fact, when we are thinking about safety. And then lastly, a big class of tools, and this might hopefully be one of the few jargony terms I have here, the distributionally robust optimization, which essentially says if we want to be prepared for what the future has for us and have better mitigation strategies, we want to possibly look at uncertainty in the distributions themselves and not just basically kind of thinking that with all of the data that we have, with all of the knowledge that we have, the data, the inputs into our uncertain systems are supposed to be coming from a certain distribution, but rather thinking that those distributions themselves could be going through uncertainties. So for each of these 4 messages, I have a couple of slides here today. I mentioned that I'm going to give examples about what I mean when I say current practices could harm us in the long run. And this one was actually the first really interesting study that I came across by researchers in University of Michigan who simulated the tsunamis and this particular study was in a coastal place in Japan called Taro. And they wanted to see the effect of having seawalls for the purpose of reducing damages on the communities. So what they looked at was if we knew what we know now would be the case in the next 300 years, how could we choose the height of these seawalls so that we can have the kind of best safety measures in place. And if you look at the graph on the left, they found, obviously, again, if we know what we know today, would hold true for the next 300 years, that the higher that your seawall is, the more safety you will gain. But then they also looked at a case where the future would be drastically different from today, and we would have more of these black swan effects or events in tsunamis. And what they found was that, in fact, as you increase the sea level rise, you might end up with more damage than more safety. And that's because you will give the people who live in those communities a false sense of trust. So they would kind of have more developments on these larger seawalls. And if you have more black swan events, you could lose more lives as a result. So this was kind of a very interesting study. And secondly, I think the other study by some of you here really looks at the human manipulation on the barrier islands or similar structures where we want to reduce the risks that these storms have in our infrastructure, in our roads, by building dunes or bulldozing off the overwashed sands that the storms could bring onto our developed areas. But as a result, and again, looking on the plot on the left, what we see is that by these current strategies, we could, in fact, in the long run, harm, and this is more due to just the way that the physical system works, even without considering the high uncertainty in the weather and sea level rises and so on, that as a result of these current practices, we could in fact put ourselves in a more vulnerable place because the natural system would actually kind of correct itself by keeping the elevation level kind of steady, in relation to the sea level, whereas by the human manipulation that I just mentioned, we could actually be at the risk of having lower elevation and hence higher risk. And so you can see also on the left that the flooding events simulated over 4 decades shows that these coupled systems where we are bringing in these mitigation strategies could actually be working against what we were hoping to gain. Now I want to talk about kind of zooming out simulation. Stochastic simulation as a concept. Monte Carlo as I'm sure many of you here are using these tools for analysis of highly complex physical systems that you're working with. And just maybe to list that they could be very strong tools, not just for modeling and prediction, but also for evaluating high risk events and extreme events, as well as understanding what would they be most sensitive to when we are validating or building these simulations, so that we can pay extra attention to those parts of our simulation. And most importantly, they can be used for decision making and optimization, which is the area that I'm focused on. So as you can see, there's this input model that comes from a logic that we can gain through knowledge and expert domain opinions. And then we can run our simulation for a specific scenario, say n replications. And then we can look at not one, but n outcomes that would kind of approximate the distribution of the output for us. So in fact, we would have a distribution of the output, and then the question becomes, how do we really quantify these outputs in order to be able to make decisions or evaluate risks or sensitivities? So for one of the examples that I gave before, perhaps it helps to think about what each of these terminologies would mean. So I talked about models, which consists also of input variables and parameters, but the models are these mappings that transform, your inputs to the output. So you can think very broadly that they're mapping the future climate to the future damage, or maybe in the case of the sea level rise and the elevation, you can think of the future sea level rise as the input and the elevation as the output. You could also be using surrogate models that are just computationally more tractable, like low fidelity versus high fidelity models here. But as part of the model, you have some input variates, again, that will be following some distributions, as well as some parameters that you can learn by using some inverse studies, calibration studies that can also be complemented with knowledge about the physical mechanisms. And then there's the noise or error that can come from a variety of sources. So we have the exogenous or epistemic noise, which can come from the fact that our knowledge about the system is limited. You can also think of it in general, if we were able to have, in theory, infinitely many runs of the system, we would be able to, in some sense, drive this type of noise or error to zero and get rid of it. But there's a different type of noise, that's the endogenous or aleatory variability, which is pointing to the distribution of the inputs. So that distribution exists, and no matter how many data points we gather or how many times we run our simulations, we cannot get rid of that variability. But there is something that I'll talk a little bit about later, which is about the uncertainty in the inputs when we actually choose distributions on the input. So again, this could be the sea level rise that could be distorted and could be modeling or misrepresenting the actual distribution. And lastly, we have the output, and in a very general sense, we use expected values. So we will be looking at average outcomes. But again, for cases where we're talking about high impact and extreme outcomes, we probably want to be looking at different kinds of quantities that I will talk about in a little bit. Okay, so the second message is that we're going to have a lot more extreme events, and we don't have enough data to build really good models that could predict those. So this is probably one of the main use cases of uncertainty analysis. In particular, for the case of rare extreme events, there are certain sampling schemes, very smart ways that we can tweak the distribution of the data that we have with this class of methods called variance reduction. And what they do is they manipulate intentionally the distribution of the inputs so that we can generate more of those catastrophic events and can study, with less variability, their impact on our on the system that we're interested in. But of course, because we are changing the reality in that case, we also want to find nice ways to correct those analyses or estimates that we get back to be able to kind of claim that we have unbiased estimates of the outcome. So again, think about estimated outcome as the elevation or the cost as a result of that, maybe in long term. And we would be interested in looking at ways by which we can actually reduce the uncertainty that there is in the outcomes by changing the distribution on the input side. And two very popular methods for that are importance sampling and stratified sampling. So maybe in a very crude sense, you can think of both of these doing kind of similar things, which is focusing on regions of the input data that would be most important or most impactful for our estimate purposes. So like this figure here in the center is an example of importance sampling. So if you think of this dashed line as the original input distribution, what importance sampling does is that, in fact, it tweaks the distribution completely. You can see that it's now not a unimodal distribution, but it does that because there is evidence in this case that we want a lot of data to be concentrated in this area and in this area. So based on that analysis, we come up with this new measure or probability measure distribution, but then at the end we need to kind of correct it back to be able to make unbiased inferences. The other method is the stratification, which I think is more intuitive, because what you're saying is that instead of doing random samplings from the data, I'm actually going to, based on similarities, put the data into strata or partitions, and then based on some properties that these partitions have, for example, if I have partitions that have more data in them, so I am able to get more samples from them, I can do that. And then for those that I can't, I keep the ratios at bay. And as a result, it turns out that you can also control the variability. And this can be very effective for, like I said, the case of rare events and extreme events. There's another class of algorithms here that is more in the applied mathematics side, the extreme value theory, that says, and this is the only mathematical expression I have here in these slides, but it basically looks at the probability, maybe that you can think of it as the excess, given, so you already know that you are in a bad region for your random event, but then you want to see probability of having a high threshold. And there are mathematical results that say these kinds of probabilities converge to something that we know very well called generalized Pareto distribution. And because of that, we can make a lot of nice inferences on such events. The other area where that particularly deals with the data and the shortage of data is the uncertainty in the data, which we call input uncertainty. And that essentially arises when you have input distributions that are noisy. So your data is very noisy. And the idea for input uncertainty is that when we get our predictions from the output of our simulations, we need to acknowledge that there is the variability due to just the system being stochastic, but also there's variability because we may not have found the correct uncertainty model for the inputs. And if we ignore that second part, or the input variability, it's very possible that we can underestimate the overall variability of this system. And as a result, if we were, for example, going to be doing optimization or decision-making here, underestimating the variability could lead to suboptimal decisions. So to hedge against the overall risk, it's important to quantify also the variability that's in the inputs. And again, here in this case, in this figure, I point to inputs as parameters, but you could think of parameters. What I mean by input parameters is if I was going to assume that data is following a certain distribution and that distribution has a parameter, but it could also be non-parametric, and we could still be studying input variability for non-parametric models. Okay, so now that we've learned about on the input side where uncertainty could be playing a big role, we can now go back to that same figure we looked at earlier and see how can we really quantify the output based on the focus that we have on safety, right? In particular for the hosts. So as I mentioned, it's very common in Monte Carlo methodology that averages and standard deviations are used to describe the behavior of these output that is distributional. But in safety cases, we might be looking at tail probabilities. So, if thinking of the elevation being less than a threshold would be a tail probability. And the other way that we can think about it is actually averaging all possibilities. That's, like I said, the classical way of quantifying the outputs versus averaging only the bad possibilities. So it's also known as conditional value at risk in economics, where you only look at the bad outcomes or outcomes beyond a threshold, where you can consider a failure, perhaps, and then look at an average of all of those outcomes as an outcome. So clearly, when we think about these new ways of quantifying the output of our simulations, we are enabling, higher chance of resiliency for the underlying systems. And then one last thing, circling back to the input side. So we are talking about tail behavior and uncertainty quantification. A lot of times uncertainty quantification is a term also in applied mathematics, where we basically talk about, and maybe I should go to the next slide to talk about this. We're talking about not knowing exactly what the causal model or physics-based model would would respond to a certain input. And based on that, we do data assimilation and integration with something such as Gaussian processes. And I'm not going to go into that much, but suppose in the figures below that somehow we believe that our system y of x in this case has that causal model or physics-based model, but we also want to kind of integrate the information that we get from the data by having a Gaussian process kind of wrap around that initial prediction model, and therefore use uncertainty quantification. And this is an area that I haven't really worked all that much in. The area that I am getting more familiar with is, again, the input data uncertainty and logic model uncertainty. So if I can say something about how much, as a result of a change in the input model, I would have to basically pay in the output side. In some sense, I can do a quantification of uncertainty as well. Okay, and this is the last kind of class of methods, the distributionally robust decisions. So we would like to be able to hedge against uncertainty as much as possible. And it seems to be relevant to think about even the distributions of all of our inputs having uncertainties. So at the bottom of the slide, I have an optimization problem where I'm looking for decisions that would work well for not just a single distribution, if P is a distribution, probability distribution, but on a series or set of distributions that I think are plausible. And I'm going to call those uncertainty set or ambiguity set. And being robust in this sense may give me a whole, if I was going to solve this optimization problem as opposed to a classical optimization problem where I say that I believe I know what the distribution is, I might get more conservative responses here or solutions here, but that at least I can have some statistical guarantees that can be more effective in the presence of high uncertainty. So as I mentioned, we want to be searching for solutions that optimize the problem under worst case uncertainties, if you will. And hence we are going to be having more conservative solutions. I did also want to kind of connect the distributionally robust optimization as a class of optimization problems with all of these other areas. There's a huge application for model calibration, extreme estimation, and input error quantification that I mentioned a little bit earlier. So going back to the first slide, where we talked about the main takeaways of this talk, I feel like maybe one thing to remember out of all of this, because some of the stuff that I mentioned very briefly may be overwhelming, but maybe in the black box, you can kind of think about the possibility that, you know, as a result of including these insights, you might be better to go with a choice that is not the best on average, but has less variability, again, in the long run. Or you might be better off with choices that are optimal to worst case scenario generators or distributions, even though they're conservative. Despite that, you would see in the short term, they're not favorable, either to the habitability or economy or other measures. So with that, I think I would like to acknowledge some of the figures that I have used from Henry Lam in Columbia and Johannes Royset from Naval Postgraduate School. That's my email address and my website. Thank you.
Thank you, Sarah. We only have about 2 minutes for questions. So if anyone wants to unmute themselves and ask a question for Sarah. You're getting lots of rounds of
Hello,
applause.
can you hear me? Hello. Hello.
Hi, Roland.
Good evening, Nigeria time. Thank you, Dr. Sarah, for the presentation. I really enjoy it.
You're welcome.
The question I want to ask is that this is your model, the model that you just show us. Can it be locally adapted? For example, if I want to apply maybe along the West Africa coast, can I be applied to maybe what is happening, for example, in Nigeria coast? So can we use the model to study what is happening on that coast, or is made for one particular region? Thank you.
Thanks, Roland. Did you get that, Sarah? He also put in the chat.
Yeah, I think what I understood was if we can take the models and then apply them to Nigeria or other locations. Is that what you were asking for, Roland? Okay.
Yes,
Yeah,
yes.
okay. That's a good point, because that actually does speak to why something like distributionally robust modeling might make sense, because you might spend a lot of investment building a model that would very accurately predict a certain region, but it would probably do poorly for other regions. So if you look at the way that you're training the models by having these uncertainty sets instead of like really closely following the data for a single region, you might get more robust models that could be, when I say robust, they could also be like spatially robust. So that is a possibility.
Thanks, Sarah. Any other questions? We have
Sarah, can I just jump in? Wonderful presentation, and I look forward to having more conversations in the future. But one thing I wanted to toss out there was when you're turning the analysis to think about safety, how does that change the way we think about benefit cost analysis, where we're used to thinking about what are we willing to spend to get some expected benefit, but in the safety world, that now it doesn't have the direct analog. And I'm just wondering if there's a literature on this, or if you've thought about it.
Mm-hmm. Thank you for that question and comments, Martin. So yeah, I came across this not too long ago, where the kind of old way of uncertainty quantification, which I mentioned was with expectations and standard deviations, could be misleading. And there are a few examples in the literature where mathematicians have come up with these artificial distributions that have the exact same mean as standard deviation, but they look very different. And if you were interested in tail probabilities or probabilities of failure, which would be the case for the safety measures, you could see that just by looking at the averages and standard deviations, you wouldn't be able to differentiate if one is better than the other. But by looking at, obviously not the entire distribution, but at least a portion of the distribution that is relevant to the tail behavior, you would have a very different analysis of the two distributions. But I can definitely give you also some papers. I would also point to Johannes Royset, the second person that I had in my acknowledgement. He has a nice set of papers that address that. Thank you.
All right. Thank you, everyone. We'll see you back here. It looks like October 28th, so a month away, for a synthetic discussion on these topics. We can really dig our teeth in and start to think about transdisciplinary science. So thanks, everyone. Have a great week.
Thank you.
Thank you.
Thank you.